All right, good day. Now, I'm not sure if I'm going to make this just one video or this should be part one of two, but for today's video, what we will do is start with solving simultaneous differential equations, right? And so technically this can be done using a technique called the plus transforms, right? Sadly, we did not get to that, right? Because of the airtime silence, right? But today we will now tackle, right, how it is possible to solve systems of simultaneous linear differential equations using vectors. More specifically, eigenvectors and eigenvalues. So we will have two examples, one with a 2 by 2 or one with two unknowns and two equations, and another one here with three unknowns, three equations, right? Our goal in here is to just get the general equations or general solutions for both of them, right? So they will include two arbitrary constants, right? There are two arbitrary constants in here because each of them are going to be first order differential equations. So each of them should have one arbitrary constant. That means there will be two arbitrary constants in here, and of course in here there will be three. Okay, so let's begin. How do we even start with this equation, right? Or these equations, right? The thing is, just like before, right? If we zoom out a little bit, right? We have just finished our discussion on simultaneous equations here. So maybe we can take a little hint and maybe turn it into a matrix form, right? In this case, we can do 1, 1, 4, -2, and then we can have xy in here. On the other side, however, we will have, right, dx over dt, which you can just say is x dot, and dy over dt, which you can just say is y dot. Now notice that this thing, say for example, if we call that our variable vector x, this thing we can now also kind of call x, but it just so happens that everything in here has been derived with respect to time. So technically, the vector itself has been derived with respect to time. So that now that is x dot. And this is just our sample, or rather our coefficient matrix A. And so now you expect something like this. Ax is equal to x dot. Or more specifically, x dot is equal to ax. And if it were just a normal, right, just a normal differential equation, you would definitely understand how to do something like this, right? Say, for example, dx over dt is equal to ax. You would immediately say to yourself, wait a second, this is variable separable. Dx over x is equal to a times dt. And you will basically get, if you integrate, you will get something like ln of x is equal to at plus c, whatever that plus c is. And then you can raise both sides with respect to e, and you will basically get in here, because right, there is a specific interaction between e and ln. There's x is equal to e raised to at plus c. Because there is a plus in here in the exponent, what you can do is you can separate them like this, and now you can say that this thing is itself a constant. So there you go. And so now this is our answer. X is equal to ce raised to at. And so it's very tempting to just put this as the answer. But we have to be very aware that, well, this is not the same thing, right? This is not the same thing, right? We are dealing here with matrices, and, well, of course, matrices have their own rules. Let us try as much as possible to skip by or to get by those rules. Let's have our little guess in here, because we already solved for the differential equation version of this whole thing right here, right? But if it were numbers, or if it were just just numbers, right, instead of matrices, our guess in here would be kind of like this, right? CEAT. But in this case, I want to be very clear that this will not work as a matrix because this is just a number. So if anything, this is going to be k, right? K for constant, right? Ha ha ha. But I mean, honestly, we could just go for letter C. C, okay, you know what? C works as well. But let's make it a matrix C. And then here's the hard part to, here's the hard thing to put e raised to something t. And here we will denote this with the letter omega, right? Omega, that is the case because, well, usually omega, if you guys remember, right, is angular velocity, and it has units of radians per second, right? Radians per second. And if this is time, right, and that should be multiplied by seconds, and this usually cancels out. This is just for those reasons, right? This is just for those reasons. Okay, so the thing about this is that okay, what's the point of this, right? What's the point of this? The point of this is now, right, you are going to be able to put this into your equation in here, right? If you know that your x is this thing, right, you can put this and substitute this here. Moreover, what you can do is you can now derive it. This c will not change, but if you derive this thing, right, you will just copy it, and then you will chain rule the exponent, which will give you this extra omega. And now, if we put everything together into our original equation, into our original matrix equation, we will have a times c e omega t is equal to c omega e omega t. Now notice we can cancel, and we will be left with something that is a little bit ridiculous. Your A, which is a matrix, is equal to your omega? That doesn't sound right, right? How can a matrix be equal to a number? Okay, how can a matrix be equal to a number? Now, this is the perfect time for us to introduce an eigenvalue. An eigenvalue basically corresponds to this thing, right? Excuse me. Say, for example, right? How can a matrix be equal to a number? Or in other words, how can a matrix be equal to a scalar? This is how. If you think about, right, having a matrix be multiplied to another matrix, say for example, just the letter V. This, okay, let's change the symbol. Let's make it lambda. This is the standard for eigenvalues. That lambda can act as the same thing, right, for scalar multiplication. This, kumbaga, this is scalar multiplication, right? And basically this value of lambda, this is matrix multiplication, right? And this lambda can achieve the same effect via scalar multiplication. So in essence, this is as close as a number is going to get to represent, quote unquote, represent a matrix. So this lambda in here, right, the lambda is what we call the eigenvalue, right? The eigenvalue. And in this case, right, your v in here is what we call the eigenvector. If you're wondering about the name eigen, that is the German term for true, right? So a true value, right? Anyway, right, how are we going to get this eigenvalue? Well, right, at the very least, what we're going to do is just do something like this, right? We want to be able to recognize that this a, or rather this lambda right here, is as close to lambda as it's going to get. So how are we going to turn this thing into a matrix? Well, the best way, or the easiest way, is to just multiply it with the matrix's version of the number 1, right? The multiplicative identity, the unit matrix. And so if you're going to do something like this, right, at the very least, you need to make sure that, well, this makes sense, right? This makes sense. And so, right, okay, by the way, this is not just 0, this is a 0 vector. right? Everything in that matrix is just zeros, plain zeros. So if you take the determinant of all of these, of both sides, what you will get is basically the determinant of, of A minus lambda I is going to be the determinant of a zero vector, which, surprise, surprise, is zero. So this is the first thing that we should look out for, right? This is the first thing we should look out for. And so, before I even start, right, solving for this equation, I just want to give you guys the rundown, right? So you don't have to, kumbaga, you don't have to be under so much trouble, right? Say for example, with finding the value of an eigenvalue, right? Finding eigenvalues pala in general. And so, how are we going to do this? Well, say for example, you have a general 2 by 2 matrix, which is A, B, C, D, right? What you will do is then you will try to construct A minus lambda I. In this case, what we now can see is that, or what we can now imply is that only square matrices can get eigenvalues. It's very interesting, right? So we will now have A, B, C, D minus lambda times your unit matrix. You will have 1, 0, 0, 1. And basically what you will get is this resulting thing, A minus lambda, then B, and C, and D minus lambda. Okay, now what? Right? We will now take the determinant of this thing. Determinant of A minus lambda I. What you will get is basically AD and then minus BC, right? So that's going to be A minus lambda, D minus lambda, minus BC. And let's just try and expand this thing, AD, and then minus, right, I'm doing FOIL, minus A lambda, minus D lambda, plus lambda squared, minus BC. And basically, if I'm going to rearrange this, I'm going to put this first, lambda squared. And then, as you can see, both of these things have a negative lambda. So what I will do is now I will group them out. And then I will pick out the A plus D, right, times lambda. And then I will group all of the constants out, AD minus BC. And you're like, something's going on. Right? And of course, all of these should be equal to 0, right? That was our agreed upon rule from earlier. And so now, do you see why I have grouped these two things together? This one, the one that I've underlined in blue, might be a bit more understandable for everybody. This is the determinant of your original function, of your original matrix A. Now, what about A plus D? What is A plus D? If you remember, right, a little, if we zoom out a little bit, right, a little trace, right, a trace is what we have here, right? That is your A plus D. That is the main diagonal, right? That is the main diagonal. Where did I put this here? Yeah, there you go. So your trace of E is going to be this and this and this, and you add them all together. And so now, the general formula, right? The general formula for this thing, so you don't have to go and expand this all the way, so on and so forth, is going to be lambda squared minus trace of your original matrix times lambda plus the determinant of your original matrix is equal to 0, which means you can now apply the quadratic formula to your delta. What do you call this again? To your lambda. There you go. Right? And of course, that is for 2 by 2 matrices, right? I cannot tell you anything for 3 by 3 matrices using this. Okay? But it's useful enough, right? So what we can do is we can put this here. Let's try and test this out. If our A in here is going to be 1, 1, 4 minus 2, right? 4 negative 2, our A minus lambda I is going to be equal to 1 minus lambda, and then 1, and then 4, and then negative 2 minus lambda, right? And we don't have to go through all of that work. We can just say that the determinant of a minus lambda I is going to be equal to lambda squared minus, what is the trace of this thing? Right? That is negative 1. So actually this is plus lambda minus, right? Okay, why did I put minus? It's supposed to be plus the determinant of this thing. So a times d is 1 times negative 2, negative 2 minus 4. Okay, so it really was negative. Negative 2 minus 4 is negative 6 is equal to 0. And as you can see, you can factor this out, right? With enough effort, you will get minus 2, lambda minus 2, and then lambda plus 3 is equal to 0, which means there are two values of lambda. Lambda equals 2 and lambda equals negative 3. It now depends what you guys want to do, right? Or what value you want to assign these to. But what I will do is that I will choose this as my lambda 1, and then I will choose this as my lambda 2. I'm just basically giving them an order because this order will matter later down the line. And so now you can see, or rather we can imply from this case, that there are now, based on, right, your square matrices, there are now n possible eigenvalues for an n by n square matrix. Okay, so in this case, in number 2, we will expect 3 eigenvalues. Okay, and so let's just try and have these two. From the from the eigenvalues, we can now get the eigenvalues' unique eigenvector. That is why the order is important. In this case, your C, this value, this constant C, is actually determined by the two eigenvectors. If for being very clear, C in here is composed of the two eigenvectors that correspond to your, right, that correspond to your eigenvalues. Okay, but more on that later. Let's just try and get the eigenvectors now. For lambda 1 is equal to 2, right? What we will do is now we will have this definition from earlier. AV is equal to lambda V. Our A value in here is 1, 1, and then 4, negative 2. And our goal is to find that value of V, right? So, in this case, kayo na bahala, honestly, right? U or V, whatever, X or Y, if that works for you, go ahead, right? If V1 and V2 work for you, then go, right? For me, what I prefer is actually X and Y. But this might, of course, right? This might arouse suspicion here, or rather it might arouse confusion here. So maybe just like a U and a V would be fine, right? That would be equal to 2 times UV, right? So in this case, what we would see in here is basically this thing, right? This is a 2 by 2 matrix. This is a 2 by 1 matrix. So we will create a 2 by 1 matrix as well, right? So we will get in here row column, that is going to be U plus V, is equal, and then for the lower side we will have 4U minus 2V is equal to 2U and then 2V. What now, right? What are we going to do now? Well, let's just have them and disassemble them, right? U plus V pala rather is equal to 2U. If I disassemble this, put this to the other side, we will have this relationship, which is U is equal to V. Okay, interesting. And then we will have 4U minus 2V is equal to 2V. If I put this here, we will have that same relationship. 4U is equal to 4V. Basically, if I divide 4 on both sides, we will still have this relationship of U is equal to V. What is up with that? That is actually going to be a big what do you call this? A big factor, right? Or rather a big clue. Sorry, that is a big clue for our eigenvector. Our eigenvectors can actually vary. That is why in this case, there is just this main relationship of u, v that we just need to follow. What do I mean? Say for example, right? If I know that u, v is our eigenvector in here, we just need to know that u and v are the same thing, right? So possible solutions for this could include 1, 1, I don't know, negative 1, negative 1, I don't know, pi, pi, something like that, right? All of those are possible solutions, right? That is why this is where the arbitrary constant actually comes from, right? So long as both of them are the same, you can leave it be, right? Okay, so currently in here, I'm recognizing that this is our eigenvector AA, but honestly, what they do, rather the common theme in here is just to substitute the simplest possible value. So in this case, 1, 1 works, right? You just have to remember later down the line that these two are actually variable in the sense that, well, so long as these two are the same, you can go ahead with it, right? So when I'm looking for values for eigenvectors, I'm looking for stuff like this. I just want to know the relationship between your values of u and v. That is where that comes from. Okay, and so now for the second eigenvalue, for lambda 2 is equal to square root of 3, I would now like to show you all, right? I would now like to show you all, excuse me, a little shortcut. I don't know if it will be a shortcut for you, right? But again, we go to this AV is equal to lambda V, right? And now what you're going to see in here is A is 1, 1, 4, negative 2. And then you have your V, right? Which is, again, say for example, just U and V. And then this thing is lambda. So that is negative 3 times U and V. And if we put all of these together, we will get U plus V. And then 4U minus 2V is equal to negative 3U minus negative 3V. What I will do now is that I will put these to the other side, right? What I will do now is do something like this. 1 minus 3U plus V, right? This is 1 plus 3 pala, rather. And then this is 4U and then plus negative 2 plus 3V is equal to 0, 0. Notice how both of these, right, values in here are now 0. We are taking advantage of the fact that if we do something like this, AV, right, AV minus lambda V, we will have a 0 vector, right? We will have a 0 vector. And so now what you can do actually as a little shortcut is you can just remove, or rather you can bring back the original matrix, the A minus lambda I, and you can substitute the values there, right? 1 minus lambda, 1, 4, negative 2 minus lambda. In here, if we're going to substitute the value earlier of positive 2, is that right? Yes, positive 2. What you will see is this. Negative 1, 1, and then 4, negative 4. And then you might say to yourself, okay, well, what's so different with this? If you read this, right? If you read this as if you're going to do something like this, right? X, Y, and then on the other side is just plain 0, 0. What you can immediately see is that this thing times this thing is equal to this thing, aka negative X plus Y is equal to 0, or in other words, your X is equal to your Y. That's a possible thing, right? And again, you don't have to go through this second row for you to realize that that is indeed true. They're supposed to refer to the same truth, right? Shall we say? Okay. So in this case, if you're going to substitute negative 3 now, what will happen? 1 minus negative 3 is 4, then 1, and then negative 4, and then of course, what do we think is going to be in here? Negative 2 minus negative 3 is negative 2 plus 3, which is just 1. And so, as you can see, this is very, very identical. You'll now see that this relationship should equal to 0. Okay, so this is now 4x plus y is equal to 0. And what a lot of people like to do is something like this. They substitute the simplest value possible to either x or y. In this case, x. Right? Okay, so what if your x is equal to 1? So if your x is equal to 1, then 4 plus y is equal to 0. Then your y would be equal to negative 4. And so now, our second eigenvector is possible. So now your second eigenvector is 1 because you substituted your value of x to 1 and then negative 4. But then again, you have to remember that so long as they keep this relationship, they will be okay, right? In other words, so long as they keep this relationship of b and then negative 4b, they will be fine. Okay? And so now we have our two eigenvalues, right, which are 2 and negative 3. And we now have our two eigenvectors, this one of 1, 1, or this one of 1, negative 4. We can now cobble everything together based on our guess. Based on our guess here, your x, which is basically your value of your x and your y, is equal to c e omega t. Omega in this case are your values of lambda, right? And then in this case, right, your c, right, corresponds to your eigenvectors 1 and 2. Then e raised to omega t, we'll look at that later. But in this case, we will see that your eigenvector 1 is a. Your eigenvector 2 is b, negative 4b. And then we will have your e raised to, what are the eigenvalues? The eigenvalues in this case are now going to be 2, negative 3. So you're like, what? Where did that come from? Well, we can just put this in as values of e raised to 2t. This was our first, right, eigenvector. And e raised to negative 3t. This is our second eigenvector. So they are always numbered like this. The first eigenvector will correspond to the first the first eigenvalue will correspond to the first eigenvector. The second eigenvector will correspond to the second eigenvalue. And so now it's almost done. We just have to we just have to multiply these two together. We will now have a e raised to 2t plus b e raised to negative 3t, and then a e raised to 2t plus, or minus minus 4b e raised to negative 3t. These are now our values of x and y. So this is our answer. Okay, this is our answer. And so that is a lot of work, right? But honestly, if you look at the lot of the work, if you look at a lot of the work in here, it is just algebra. Not just, but it is algebra, right? And if you follow along with the process, right, if you want to memorize, go ahead, right? If you memorize the process and if you just apply the values, so on and so forth, you will get to the final answer. And if you think that I am lying, right, that this is not the final answer, right, ax is equal to ae 2t plus be raised to negative 3t, then your y is equal to ae 2t minus 4b e raised to negative 3t. Let's derive x, right? If we derive x, we will get, right, 2a e raised to 2t and then minus 3b e raised to negative 3t. If we remember, this should have been equal to x plus y. Let's add x plus y. X plus y, ae 2t plus ae 2t. Oh, well, would you look at that? That is 2ae 2t. be 3t, and then minus 4b e raised to 3t. Would you look at that? That is now your negative 3b e raised to 3t. Now, let's try and look at our dy. Okay? dy over dt. Okay? dy over dt. That will give you 2a e raised to 2t. minus or plus 12b e raised to negative 3t. So let's try this out. What is our value of dy over dt? That should be equal to 4x minus 2y. Okay, so 4x. Okay, so 4x. So this is just 4. This is 4. And then minus 2y. So minus 2a. Let me just overlay this with other colors. 4, 4, 4, negative 2, negative 2, positive 8. And so now we will just add these stuff together. Add these things together. 4a e raised to 2t minus 2a e raised to 2t. That is 2a e raised to 2t. 4b e raised to negative 3t plus 8b e raised to negative 3t. Would you look at that? That is your 12b e raised to 3t. That is how we're going to get these values. Okay, so that is how this thing goes. Okay, that is how this thing goes. Okay. And so now we move on to number 2. Now we move on to number 2, which is essentially a little bit harder, but now we don't have to introduce things, so we can get on with the flow immediately. Right? We have this thing, which we can organize. We can turn it into 1, 2, negative 2, negative 2, 5, negative 2, 2, 2, negative 3. And then we will have here our values of x, y, and z. And of course, they will be equal to our value of x dot, y dot, and z dot. In here, we can see that again, we are looking at a times x is equal to x dot. And so we can warrant a guess immediately that your x dot, that your x is just c e raised to omega t. And just like before, this c is now composed of the 3 eigenvectors v1, v2, and v3. And this thing should be equal to, right, your e lambda 1t, e lambda 2t, e lambda 3t. That is how it's supposed to be. And so now let's find the values of lambda and the values of v. Okay, let's try this out. Whew. All right, let's first try the whole, let's first find the values of lambda in here, right? And so we will use this original vector, and let's already include the minus lambdas in them. 1 minus lambda, and then 2, and then negative 2. We'll have negative 2, 5 minus lambda, and then negative 2. We will have 2, 2, negative 3 minus lambda. And then if we put them all together, we will get the determinant, right? The determinant of everything, which is 1 minus lambda, 5 minus lambda, negative 3 minus lambda. This is going to take a while, right? So this is our first. Our second is this, right? Which is 2 times negative 2 times 2, which is negative 8. And then this is our last bit, right? Negative 2, and 2, that is plus 8. So cancel, cancel. And then next we look at the upward diagonals. We will have plus 4 because of the negative in here times 5 minus lambda. We will have this as well. And then we will have plus 4 again, right? Plus 4, 1 minus lambda. And then again, a plus 4, right? Plus 4 times negative 3 minus lambda. All of that should be equal to 0. Okay, so we're gonna have quite a little, quite a bloody kind of, what do you call this? Simplification going on here. What's good is that I can actually flip the two values here, right? Because if I'm going to flip them, I'm going to invoke a negative 1 from each of them. And honestly, I can flip this as well, or rather I can get the negative sign from that and put it in the front. And now this is plus 3. And now we will have 4 times basically everything in here. Every one of them will have a value of, or Rather, all of them have a common factor of 4. So I'm just adding everything here together. Okay. So currently we have, honestly, I'll just FOIL this first thing. Lambda squared minus 6 lambda plus 5. And then lambda plus 3. And then now you will have in here 4 times. 5 plus 1, 6 minus 3 is 3. Minus 3 lambda. Okay. So what we will have, oh, you know what? Look at this. Oh, never mind. Oh, actually, yeah. Okay. Let me unfactor that first. Oh, let me refactor that first. Just so I can show you guys that there is something going on in here. As you can see, there is a common factor here of 3. But what if I pull out a negative 3 instead? What will happen is that there will be a negative 12, and then there's a lambda minus 1. In here, there's also a lambda minus 1. It's very interesting, right? And in fact, we can remove the negative signs because we can just multiply everything in here by a negative 1, and we can remove. This will now be positive. And what's better is that we can now factor out a lambda equals 1. What remains in here is basically this thing plus 12. So that is going to be lambda squared minus 2 lambda, right? Minus 15 minus 12. Is that possible? 20, 20, oh no, this is plus 12 pala rather. This is plus 12, right? Because of the whole thing here, you're now adding all of these things, right? Is equal to 0. And now we can see that this is going to be negative 3. We will have lambda minus 1 and then lambda squared minus 2 lambda minus 3, which is now going to be equal to, you can factor that out. That will be lambda minus 3 and then lambda plus 2. Oh, sorry, lambda plus 1. Is that right? Yes, that is right. And so we have 3 values of lambda. Congratulations. We have lambda 1 is equal to 1, lambda 2 is equal to 3, and lambda 3 is equal to negative 1. So there's a lot to do. Okay, there's a lot to do, and well, we'll just try and figure this all out. Okay, let's just try and figure this all out. Excuse me. Okay, let's try. We will get first our lambda equals 1. For lambda 1 equals 1, we will have this, you minus 1 everywhere. Right, so 1 minus 1, 2, negative 2, negative 2, 5 minus 1, and then negative 2, then 2, 2, negative 3 minus 1. Okay, we will now have, for some reason, 0 to negative 2. Negative 2, 4, negative 2. And then 2, 2, negative 4. What's going on in here, right? Very curious, right? But basically, we will have here x, y, and z. Or if you want, UVW, right? Or RST. RST can work. Sige, let's try RST. Is equal to all zeros. Let's have our first one, right? Let's have our first one, which is basically 0r plus 2s minus 2t is equal to 0. So what they are saying in here technically is that your s and your t, right? If we cancel this out, if we put this to the other side, your 2s is equal to your 2t, which means that your s is equal to t. Very interesting. And so, if s is equal to t, let's just try and put this on the other side in here. For the second equation, negative 2r plus 4s minus 2t is equal to 0. If your s is equal to t, well then, I can just replace this t with an s. And what you would get is negative 2r plus 2s is equal to 0. If I put this again in here, you will have 2r is equal to 2s, which means your r is equal to s. So, if your r is equal to s and your s is equal to t, then that means that the eigenvector in here has r, s, and t all equal, aka a, or just 1, 1, 1 if you want. But everything in here will now be A. Okay. Okay. Next, for lambda 2 is equal to 3. Is that right? 3? Yes. So we will now, you know what? I'll just copy paste this. Copy paste. Copy paste. I love technology. Minus 3. Minus 3. Then minus 3. We will have here, what is this? 1 minus 3 is negative 2. 2, negative 2. Negative 2, 2, negative 2. 2, 2, negative 6. Okay, so very interesting. X, Y, and Z is equal to, or rather, we are supposed to put R, S, and T is equal to 0. And so, if we look at the first one, right, the first row, we will have negative 2R plus 2S minus 2T is equal to 0. Okay. What's so interesting about this? If we remove all of our 2's and if we put all of the negatives to the other side, we will have S is equal to R plus T. Okay, interesting. What about this one? What does this say? 2R plus 2S minus 6T is equal to 0. If we cancel out all of our 2's, we will get R minus S is equal to 3T. R plus S minus 3T is equal to 0. If we put this to the other side, we will have R plus S is equal to 3T. So how are we going to combine these two things? Okay. Let's try. All right. If, say for example, your R is 1, it's still not enough. Right? It's still not enough to solve this thing. So say for example, what is going to be your value of S? Say S equals 1. Let's try. 1 plus something is equal to 1. So your T is 0. Okay, let's try and see if this is also true for the other side. 1 plus 1 is 0. That doesn't sound right. Okay, so let's backtrack a little bit. What if instead of R is equal to 1, T is equal to 1 as well? So in this case, 1 plus 1 is, okay, let's try 2. 1 plus 2 is 3 times 1, 3. Okay, so that means that, right, the things that satisfy this is R is equal to 1, S is equal to 2, and then T is equal to 1. And again, this is not the only eigenvector that we have. We have basically everything else in here if they are scaled correctly. So this is B, 2B, and then, oops, not 2, B. So that is our second eigenvector. And for our last eigenvector, we will have, for lambda 3 is equal to negative 1, let us copy paste. There you go. So instead of minus 1, I will do plus 1, plus 1, plus 1. So we will have in here 2, 2, negative 2, negative 2, 6, negative 2, and then 2, 2, negative 2. So of course, as we can see, right, from RST, again, we see these two are the same with these two right here. So let's just proceed. Right, is equal to 0. Right, what is happening is 2R plus 2S minus 2T is equal to 0. And if we cancel all of our 2's and put the T on the other side, we will have this relationship, R plus S is equal to T. On the other hand, let's try out this thing, right? Negative 2R plus 6S minus 2T is equal to 0. If we divide everything by 2 and put all of the negatives to one side, we will get R plus T is equal to 3S. And again, let's try this out. What if R is equal to 1 and S is equal to 1? 1 plus 1 is 2. 1 plus 2 is 3. Which makes sense. That means that your T in this case is now going to be 2. And finally, our third eigenvector is going to be equal to 1, 1, 2, or basically C, C, 2C. And now we can breathe out because our guess is going to happen now. Our guess, which is x, which is the values of all three variables all at once, x, y, and z, will be equal to, right? Your eigenvector 1 is 1, 1, 1. So, or just A. And then your eigenvector for the second one is B, 2B, then B. And then for the third one, it is C, 2C. And then you will have the three eigenvalues. E raised to t, e raised to 3t, and then e raised to negative t. Is that right? 1, 3, negative 1. So that means that your values, right, that your values are going to be x, y, and z. Your functions, rather, your general solutions are as follows. A, E, T, B, E, 3t, plus C, E, negative t. You'll have A, E, T, plus 2B, E raised to 3t, plus C, E raised to negative t. And then you will have A, E, T, plus B, E raised to 3t, plus 2C, E raised to negative t. Those are your three, right? Those are your three general solutions. Okay, so that is your answer. Okay, so based on the runtime of this thing, I might choose to stop here or I might choose to continue. So there is a lot of work that needs to happen just for you to be able to solve one eigenvalue or one eigenvector problem. But hopefully you can see from these solutions that nothing really involved is happening in the background, right? All of this is very algebra based. And so that means if you're good with algebra, you're good with linear algebra. Right? And so that is the goal in here, right? What we are doing in here is basically solving a list, right? We are solving a system of equations. Well, they are differential equations, but they are still equations nonetheless. So we can employ some of the different things that we have learned from earlier, and we can apply it here so that we can solve these things in a more organized manner. Because trust me, the other one, right? The other kind of what do you call this? The other kind of solution, the one by Laplace transform, is just as messy, if not messier, right? And if you try to do this by hand, good luck, right? I really don't know what to say, right? So there you go. Those are our 47 minutes, right? Those are our two questions. And for the last bit, I will up the ante, right? For the last bit, instead of this being dx over dt and dy over dt, we will now up the ante and we will now make this second order differential equations. We will now make these things second order differential equations. So stick around for that. Hopefully you guys do, right? And I will see you on the next one. Thank you very much.